Hello, welcome back to Discrete Calculus with Wolfram Language. I'm Alistair Forsyth, and this lesson will go over sequence recognition. So to start with, we have some techniques that you can do by hand. For sequences with polynomial formulas, the technique can be generalized fairly easily. Our generalized technique for sequences with polynomial formulas goes something like this. First, you should look at the differences between neighboring elements. If the difference is constant, that means we have a linear function. Secondly, you should look at the secondary differences. If those are constant, then we have a quadratic function. Next, we can continue this process until the differences between neighboring elements are constant. Doing this should give you the nth derivative of the sequence's function, which can be used to find the function itself. Finally, once you have that, you can write a polynomial with the corresponding degree and then fill in the coefficients by plugging in known values. The reason that this process works is because it examines the derivative of the sequence function. Now this relies on the fact that a polynomial function of degree n will have a constant value for its nth derivative, which we can then use to find the coefficient for the most significant part of that function. Now to demonstrate that this technique works, I'll run through an example with a random polynomial. Starting at index 3, we have this sequence: 49, 89, 141, 205, 281, 369, 469, and 581. Now, we can use the Wolfram language to examine the differences until we reach a constant. The immediate difference between neighboring elements is not constant, so we have to keep going. If we evaluate this a second time, we notice that the difference between neighboring elements becomes constant. We can use this to start forming our function as f of x equals 12 over 2 times x squared plus bx plus c. If you missed it, we got 12 over 2 as the coefficient of x squared because we know that the second derivative of f of x is going to be just 12, so we can take the antiderivative of that twice to get 12 over 2 x squared. Now that we have that, we can plug in known values of f and x to give us a system of equations to solve. Here, we get 49 is equal to 54 plus b times 3 plus c. We get 89 is equal to 96 plus b times 4 plus c. And 141 is equal to 150 plus b times 5 plus c. We can then subtract the constant values from both sides of each of those equations and then turn it into the following matrix. For this matrix, the first column represents the left-hand side of the equal sign, the second column represents the coefficient behind b, and the third column represents the coefficient behind c. Doing an elementary row operation and subtracting the second row from the third row, we get negative 2 is equal to 1b, which means b must equal negative 2. From there, we can see that negative 7 minus 4b is equal to 1c. So we can rewrite that as negative 7 plus 8 is equal to 1, giving us a c value of 1. Finally, this gives us a function for a sequence that can be written as f of x is equal to 6x squared minus 2x plus 1. Writing f of x out from x equals 3 to x equals 10 gives us 49, 89, 141, 205, 281, 369, 469, and 581, which is the same as our original sequence. Now, not all sequences have polynomial sequence functions, so we need strategies for other types of functions. Here, we have a similar strategy for exponential sequence functions that goes like this. First, you can take the ratios of each element and the next. If this is constant, this means the function is of the form f of x is equal to a to the power of x. Secondly, we can examine the asymptote as the index increases without bounds. Then, finally, we can plug in known values to find the constant term, if there is one. Now this method works because for any function of the form f of x is equal to a to the power of x plus r, f of x divided by f of x minus 1 will asymptotically approach a as x increases. Now to demonstrate that this strategy works, we have an example using an exponential sequence function. Starting at index 5, we are given these kind of evil values for our sequence. To be able to use this sequence within the Wolfram language, we then just evaluate this cell. Then, to start us out, we take the ratios of neighboring consecutive elements. Evaluating this within the Wolfram language gives us something that's fairly close to being constant, but isn't quite constant. As our index increases, we can see that the ratio between consecutive elements seems to approach 2.7. So to verify this asymptote, we can then take a table of 2.7 minus the consecutive ratio for each consecutive ratio we were able to gather. Evaluating this within the Wolfram language gives us a clearly decreasing margin of error. From there, we can start with the function f of x is equal to 2.7 to the power of x plus r, and then plug in values for x and f to get that constant. Here, we know that f of 5 is equal to 150.489, so we take 150.489 minus 2.7 to the power of 5. This retrieves for us 6.99993, which is not quite there, but it's very close to being 7. So from there, we can set our estimate for the constant to be 7, which then gives us a solid estimate for our sequence function as f of x is equal to 2.7 to the power of x plus 7. To verify this, we can then write out a table of 2.7 to the power of x plus 7 as x goes from 5 to 12. Evaluating this within the Wolfram language gives us our original sequence. Now, both of those examples were fairly simple. However, with more complex sequences, that process can become really tedious. And with non-exponential, non-polynomial functions of sequences, it won't work at all. So to counteract this, the Wolfram language has many functions that can assist in finding sequences by hand. For example, when given a list, the differences function returns the differences in neighboring elements. If we take a random coefficient a and list out a times x as x goes from 0 to 10, then we can take the differences of that sequence and see that it just comes out to be a. Similarly, when given a list, ratios returns the ratios of neighboring elements. If we take a base a as a random number from 1 to 10, and then take a table of a to the power of x as x goes from 1 to 10, then we can see that ratios of that sequence will return a. Now for visualizing sequences, we have the ListPlot function, which creates a plot of the elements in a list spaced out evenly. Similarly, we have the ListStepPlot function, which creates steps in that plot. We can see how both of these work by making a simple sequence, taking its list plot, and then taking its step plot. Finally, there's the DiscretePlot function, which takes a function and x, xmin, xmax, and dx, and creates a plot of the values of a function from xmin to xmax using a step size of dx. To get a feel for how this looks, we can run DiscretePlot on the same function. All of these helper functions put together give us another strategy for finding sequence functions. When a sequence seems to have a non-exponential, non-polynomial generating function, we can first look for periods or critical points in the sequence, then graph the sequence's elements spaced out evenly, then graph the sequential differences spaced out evenly, and then repeat this process over and over again. Now, while this isn't a concrete step-by-step method, this does allow us to observe the derivative of the generating function, which gives us a much better estimate of what it might be. To show you that this process works, I've prepared a very unique sequence to work with. First, we'll evaluate this cell just to get this sequence into the memory of the machine. Then, we can go step by step through our different helper functions to try and figure out what the sequence's generating function might be. Then, we can go step by step through our different helper functions to figure out what the function of the sequence might be. First, we'll take ListPlot of the sequence, and we don't get a lot of information here. What we can observe about this is that the most significant element of the function will be positive as x grows. Next, we can examine the ListPlot of the differences of that sequence. Taking a look at this graph, we can see that there is a cyclical nature to it. However, it's still increasing as time goes on. Once more, we can plot out the differences of the differences, and then see it appears to be relatively sinusoidal. Now this already looks pretty sinusoidal to me, but if you aren't convinced, we can add the joined equals true option to our ListPlot function. Now let's think about what this process has told us about the function so far. We know that the first derivative of the function is mostly positive, and we know that the second derivative of the function follows the form a sine of bx plus c. Now to learn more about this sinusoidal component, we can write a table of the sequence minus sine of x with the indexes adjusted. This table comes out to be non-constant, so we'll look at the differences of this table. Now looking at this, the primary differences are non-constant, but it looks like the secondary differences might be. So naturally, we look at the secondary differences of this sequence, and we see that it's constant. So what we now know about this function is that it has a component that is sinusoidal, and the component that is not sinusoidal has a second derivative that is constant. Now to see what this constant actually is, we have to multiply by 4 because we took the differences of neighboring elements twice. And this comes out to be 0.05. Now working backwards, a simple function whose second derivative is 0.05 could be 1 over 10 x squared. This then gives us our first full guess at what the sequence's function could be, which is 1 over 10 x squared plus sine of x. Listing this out in a table and asking the Wolfram language if this is equal to the original sequence returns true. Now this is really cool to me because taking this sequence and trying to find a function for it by hand is really difficult. However, using the Wolfram language, we can find a solution while still doing most of the mental work ourselves. Moving on, we have some more functions within the Wolfram language that can help with sequence recognition. For example, the FindSequenceFunction, when given a list, returns the function generating the list according to the Wolfram language. If we give it the Fibonacci numbers shifted over by 1, it'll return 1 plus Fibonacci of n. Similarly, if you give the FindSequenceFunction corresponding values, it'll attempt to find a function such that f of n sub I is equal to a sub I. Giving this 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32, it returns 2 to the power of n. Finally, there's the FindGeneratingFunction, which returns a function whose nth series coefficient is a sub n. Giving this -1, -1, -2, -3, -5, and -8, it returns 1 over -1 plus x squared. Now if the concept of these generating functions is unfamiliar to you, that's great because we have a video coming up on generating functions. Next up, we have the FindLinearRecurrence function, which returns the minimal linear recurrence generating a given list, if possible. If we give FindLinearRecurrence 5, 11, 17, 23, 29, and 35, it returns 2, -1. To show what this is actually doing, we can take RSolve of that recurrence, taking f of n is equal to 2 times f of n minus 1 minus 1 times f of n minus 2, and then plugging in our first two constants. Evaluating this gives us f of n is equal to -1 plus 6 times n. Finally, if we write this out in a table, we can get -1, 5, 11, 17, 23, 29, and 35. Somewhat similarly, the FindRepeat function finds the smallest repeating sequence within a list that repeats itself to generate the list. To give a fairly concrete example, if we take a table of sine of n as n goes from 0 to 20, incrementing by pi over 8, and then we take the FindRepeat of that sequence, we get a table of 0, 0.382683, 0.707107, and so on and so forth. Now the overarching point here is that this function notices that not every chunk of this sequence is unique and highlights the chunk that describes all of the rest of the sequence. Finally, we have the RSolve function, which returns a function matching a given recurrence relation. If we give the RSolve function the recurrence relationship for the Fibonacci sequence, it will actually give f of n is equal to c1 of Fibonacci of n plus c2 of Lucas L of n. Now the reason it does this is because we actually didn't give it starting values for the Fibonacci sequence, which means any sequence that is described by this recurrence relation could be the Fibonacci sequence. However, it could also be any linear combination of the Fibonacci sequence and the Lucas number sequence. To adjust for this, we can actually give the RSolve function a system of equations. So we first define the recurrence relation, then define the first two elements. Now what this spits back to us is f of n is equal to 1/2 of Fibonacci of n plus Lucas L of n. Now this makes sense because a keen eye might notice the first two indices that I put are not actually the Fibonacci sequence. Finally, we have the RSolveValue function, which is the same as RSolve, but it returns the definition of a of n by itself. So if we give this RSolveValue function the same system of equations that we had before, it'll return 1/2 of Fibonacci of n plus Lucas L of n. What I'd say is probably the most common strategy in analyzing large sets of information in the real world is actually linear regression. Basically, what linear regression is taking a data set with a dependent and independent variable and looking to find the equation f of x sub I is equal to mx sub I plus b such that f of x sub I is roughly equal to y sub I. An important distinction here is that oftentimes we aren't looking for an exact sequence function. However, we're looking for a function that roughly describes the data correctly. To do this accurately, we need to minimize the amount of error we have in any given x sub I and y sub I. To do this, we can write least squares regression, which takes the sum of the squares of our error. Now, there are a lot of important equations here, but for the sake of time and because they're not directly applicable as much to this course, I'll go through them pretty fast, but feel free to pause the video and dissect these equations yourself if you're interested. So taking this error and minimizing it using the partial derivatives of q sub f with respect to m and b gives us these two formulas for m and b respectively. Now within the Wolfram language, we have the function LinearModelFit, which performs linear regression on given list values. So if we take a table of x, 11.76x plus a random integer from -5 to 5, and then we take LinearModelFit of that sequence, x, we get a fitted model. We can then plug this fitted model into its own table and retrieve roughly the same values that we got from the original table. Now you might look at the first index and notice, oh, that's off by more than 1. But I'd like to remind you that this is actually the worst case scenario for something like linear regression, where each individual index is added with a random integer. So in my opinion, the fact that we can make a function that describes this sequence relatively correctly, even though it's, half of it is random, is really cool. What's even more cool is that linear regression is not the only type of regression. In fact, within the Wolfram language, NonlinearModelFit does the same thing, but with nonlinear regression. Now, there are a couple different types of nonlinear regression, but the main ones I've seen are f of x is equal to b sub 0 plus b sub 1 x divided by 1 plus b sub 2 of x, and f of x is equal to b sub 0 times x to the power of b sub 1. And finally, f of x comma y is equal to b sub 0 times sine of b sub 1 plus b sub 2 of x plus b sub 3 of cosine of b sub 4 plus b sub 5 of y. Now to demonstrate how this works, we can take a table of x comma 13x squared minus 2x plus a random integer from -2 to 2, and then take the nonlinear model fit of that sequence, give it the general form for our nonlinear function, and then a comma b comma x. We can see that it's surprisingly accurate. And now this isn't to say that you should be surprised at the accuracy of decades-old strategies. However, it's really interesting that you can give it a function like 13x squared minus 2x plus a random integer and give it a different form of nonlinear regression. You can still get a very accurate answer out of it. Well, you've made it to the end. In this lesson, we covered techniques for creating functions for arithmetic and geometric series by hand, useful Wolfram language functions to supplement those techniques, and linear and nonlinear regression using the least squares method. As mentioned earlier, in the next lesson, we'll cover generating functions. Again, I'm Alistair Forsyth, and thank you for watching. Bye-bye.